Welcome back to the classroom. My name is Mr. Wong. Today we'll be looking at technology and space as a part of our module Earth and Space for Year 10 Science. Our lesson intention today is to describe some technology developments that advance our understanding of the universe. We're going to list these examples and we're going to look at how specifically they contribute to our improved understanding of the universe. So let's get started. The technologies we're going to look at today are mostly focusing on the first three, and then the next lesson we can look at rockets as well. But in terms of technologies that have improved our understanding of space, we have the telescope, we have space probes, we have rovers, and obviously rockets, where we can actually put astronauts on and have them go into outer space to investigate different things about the space. Alright, when it comes to observing space, everyone would know we are looking at telescopes. So the first telescopes that were actually used to look into space was back in the early 1600s, and this is one of the very first uses of the telescope. It's known as an optical telescope. We'll go into a little bit of detail why. And it was used by a man called Galileo Galilei. So in terms of the contribution of the optical telescope, optical stands for optics, and we refer that to visible light. So as you would know, there are many forms of light. There's infrared radiation, there is ultraviolet radiation, and then you have the colors of the rainbow. That's what we call the visible spectra. It's the light that you see, and that's what optical telescope is observing light that we can see. So Galileo made some observations that created doubt in the accepted model of the geocentric idea that Earth was in the center of the universe. As you would know, this model was accepted for about 1,000 so years by the church. And the reason why the telescope helped us solve this issue or put doubt to the geocentric model was because firstly they found Jupiter has 4 moons orbiting around it. The whole concept of the geocentric model was the Earth was at the center and everything rotated or orbited around the Earth. By having moons around Jupiter would mean that Earth wasn't the only thing that had things orbiting around it, and so that caused doubt that that Earth was at the center of our universe. He also demonstrated that the moons had craters, valleys, and mountains, which broke down the concept that all the different planets in the sky or all the celestial objects were perfect spheres. It also observed the different phases of Venus, which you could see from the moon. So if the moon had different phases and Venus had different phases, then surely that needs to be caused by something besides them orbiting Earth, supposedly. And so these evidence supported the idea of Nicholas Copernicus, who was about one generation older than Galileo, of this heliocentric model. So they went from a Earth-centered model of the universe to Sun being at the center at the universe model. When it comes to how optical telescopes work, this is how you can see it here. So there's going to be 2 concave lenses, as you can see here. These concave lenses help focus the image. So you have light coming through the big lens here. This gathers the light and bends it into a smaller component. Light focuses here, so this is going to be the point at which you see the sharpest image. Okay, and then you have a small lens in this point here, which magnifies and focuses light for your eyes. So it will shrink the image down with a larger lens, but obviously we don't want it too small that we can't see, so that's why we have a second lens to help us out there. And by having the second lens, that will focus the image, so we'll make it a sharper image and make it more visible for you to see. Obviously, these telescopes are really good at allowing you to see different parts of space. We have other types of telescopes. One is the radio telescope. So these big dishes here. The reason why they're called radio telescopes is because they're trying to, instead of measuring for visible light like the optical telescope, radio telescopes tries to measure radio waves, which is also a different type of electromagnetic radiation. So it will detect very weak radio waves, and these concave mirrors that you have here, when you have these radio waves coming into the dish is curved in this manner because it's trying to allow for the rays of light to bounce off the center of the dish and redirect itself to one focal point. Okay? By refocusing it in one particular focal point, that will strengthen and amplify your signal, and then that is collected by the dish and it's taken by the receiver, and we can use that to display images or other types of information. You would know these kind of satellite dishes because we use these for, TV, cable TV. If anyone owns Foxtel or any form of cable TV, you will need a satellite dish like so, and that's kind of the reasoning of its design, taking the signals that way. In terms of astronomy, this is probably one of the most significant findings that these radio telescopes have helped us find. This is known as the cosmic background radiation. Okay, the actual color of this should be invisible to us because it is radio waves. So we've actually used digital programs to reconvert the radio waves into colors of light that we can envision. You can see the blue areas are where it's very cold, relatively speaking, and then the brighter areas where it's relatively warm. Now the reason why we call it the cosmic background radiation, because we believe this is the very first forms of energy produced when the Big Bang occurred. We'll talk about the Big Bang later on, but that's what we theorize as the spot in time where the universe began to expand. And in that expansion, a lot of energy would have been released. And so this radiation, cosmic background radiation here, was the predicted component of that expansion that we see. It wasn't at the very instant in which the universe began to expand, but it was quite close to that time period. Okay? And a little interesting story with the actual radio telescopes that were detecting it was originally they got these really weak patterns that were being detected, and they weren't quite sure, or the scientists weren't quite sure at the time whether or not they discovered the correct thing. So they had to look at their radio telescope, and they found a bit of pigeon poop on the telescope. So they initially thought it was because of the pigeon poop that they were getting these weird, weak background radiation. And so they had to clean it up, wash it clean, dry it, and then try and use the detector again. And what they found was the same signals were still coming through. And that's when they actually decided there must have been something a little bit more specific than just potentially bird poop interference. So that's a little story for you there. If we then go a bit further, we have space telescopes. So the most well-known space telescope would be the Hubble telescope, which is this one here. It's worth a few $1 billion from memory, about $2 billion. And it's the most sophisticated telescope you'll find on Earth. It is also one of the most sophisticated cameras you'll find on Earth as well. This is one of the images taken by the Hubble telescope. It's known as the deep space or the deep field, and it's just a really tiny section. You can imagine like a little pin drop if you were looking into the night sky and you looked at a tiny little pin or tiny little point in the night sky, this is what all these stars are essentially showing you in this tiny spot. This image was taken back in the 90s. And so let's go through a little bit more detail about space telescopes. So obviously with telescopes, you can see the different images in space, but you don't have anything that can record the image that you see, okay? And so what happened was the astronomers invented a thing called the charge-coupled device. What would happen is the light ray would bounce off the mirror of the telescope, and that will be collected as pixels of images. Now, if this sounds familiar to you, it's because this is the same technology you actually use to record images or take photos using an actual camera or using a phone camera. Okay, so the charge-coupled device converts electromagnetic radiation into some kind of digital information that can be processed. So you can actually use these little signals to generate an image that you can actually process and see. The early application was originally for astronomy, but now obviously it's used in everyday society. So the fact that you can take photos with your camera or from your phone, it's because of space travel. The importance of this invention was acknowledged in the 2009 Nobel Prize in Physics. Credit that for its invention. So it shows the kind of importance it had to astronomy and just the world in general. So in terms of how it works, you have these really huge mirrors collecting millions more times light than the naked eye and focusing it onto these little CCD chips. Basically, it collects a lot of pixels of information over a period of time, and then it converts an electrical signal being sent to the computer, which then converts these pixels into an actual image of different brightness depending on the quantity of pixels in a given space. So that's what it has. And like we said, it's because of this device we're able to take images of space and take those images of the deep field, different nebula, and all this kinds of stuff. And so that's the deep field that we look at. It's a very tiny, tiny space in our universe, and it was just by luck and just by chance in which scientists decided to shoot that really tiny spot in space to have a look at what is there. It's an incredible discovery at the time. Right, the next one we have is space probes. So you can think of these as quite similar to, in a way, telescopes, in a way, rockets as well. So instead of sending telescopes out into deep space, you can send probes, which will then send signals back onto Earth. These are, I would think, a little bit cheaper in comparison to the actual Hubble telescope. So probes travel at a great distance to study a wide range of features on planets, moons, asteroids, and comets. There are no astronauts on these probes, and they send back images through radio waves, which are, again, converted by computers into a proper image. The most famous probe will probably be Voyager 1, which was launched by NASA in 1977, and it was part of the program to study what the outer edges of our solar system was like. So in February 1990, the 14th of February that is, so it's Valentine's Day, Voyager 1 actually took an image, and this is the image here, what we now call the pale blue dot. So here where I circled, you can see a really tiny sort of blue dot here. That point there is the planet Earth. This image was taken 6 billion kilometers away from Earth, and as you can see, there's all these little faint lines of light going through. These light kind of frames of light is just light that was scattered because the image was taken very close to the sun. You might see other little background features, and that's just more to do with the little artifacts caused by incredible magnification of the image. In August 2012, Voyager 1 entered interstellar space. What we mean by interstellar space is the beyond the Kepler belt. So beyond our solar system that we look at. So in 2012, it went past our solar system. It took it at least 35 years to take off to that distance. So you can see there. So now that it's left our solar system, it's moving towards a nearby star. That's the code for it, which will take at least 17.6 light years away from Earth. So even then, it'll still be about 17.6 light years away from Earth before it reaches that. And in saying that, the probe itself doesn't travel at in terms of the speed of light. So it would be a much longer period of time than the so designated 17.6 years. The last type of technology we're going to look at for today are what we call planetary rovers. Now, you might have seen these images from little rovers that you might see on Mars, and that's essentially where they deploy them. So instead of sending astronauts into space, where training the astronaut can be quite expensive and their safety can be at quite a significant risk, you can make that a much easier journey, and you can allow for a much greater diversity of data collection by sending these rovers out. Because if you send an astronaut, there is a limitation of how far they can go anyways once they land on the planet or on the moon. Whilst the rovers, they can go for quite a fair distance. So they can be partially or fully autonomous. So if they're fully autonomous, they can just be self-controlled. They explore the land for you, much like those fully autonomous vacuums, little mini vacuum cleaners. Kind of the same idea there. I'm not sure if those are established because of these rovers, but we never know. So it's an exploration device that helps you collect different data sources on Mars, basically. So some really interesting discoveries the rover has seen. We found minerals of hemite. So hemite is a salt compound, basically, and remember, salt is just a metal and a non-metal. These minerals typically form when there is water. So by that evidence, we can probably work out that at some period of time on Mars, there must have been some form of water. Okay? Or else there wouldn't be these kind of minerals forming on Mars. Now, the reason why Mars is basically red soil of nothingness is partly to do with the fact that acidic water was soaked into the soil, so acids formed over a period of time, and that kind of degraded all the nutrients, so that makes it very difficult for life to survive on a planet like Mars. In another location that we see here, we also found high concentrations of magnesium and iron carbonates. And there was evidence also that if we have such a high concentration of these minerals, that would have demonstrated that there was a carbon dioxide atmosphere at some point, much thicker than what it is now, which is literally nothing. And the fact that we probably would have found quite neutral pH water. Other things that the rovers have found are ancient hot springs. So in certain locations, this is the image of the ancient hot springs. They found 90% pure silica. Now, silica on Earth usually only forms when there are hot springs or hot steam vents popping out of the little craters of areas. So the fact that we can find these silica compound or silica elements would probably demonstrate we have hot springs out of really long period of time beforehand. There's also evidence of ancient volcanoes, as you can see here, and that would create all the little craters and explosions, aftermaths that we see on Mars nowadays. So that concludes our lesson on technology and how that has improved our understanding of space. If you found this video useful, give it a like and subscribe. We'll continue on for more lessons about space in our next lesson. Till then, take care.